For this last batch of examples of sequences, we're going to try to work backwards. Well, maybe not backwards, but instead of giving an explicit formula for each sequence, we're given the actual first several terms of the sequence, and we're tasked to figure out what the pattern is. So some of these are going to be easy, some of these are going to be more challenging. I challenge you to try these on your own and then check with the video and see how well you did. Okay, but for all of these, we're going to assume that each sequence starts with n equal 1. Okay, that's not a requirement, but it's a nice convention. So in other words, in 3a, a sub 1 equals 3, a sub 2 equals 8. We're not going to start with a sub 3 equals 3 and a sub 4 equals 8. We could, but why would we? So anyway, that means we have to figure out an expression such that when we plug 1 into the expression, we get 3, 2 into the expression, we get 8, etc. So it might help to create a little, whoops, create a little chart here where we list the n values on the top and the a sub n values on the bottom. And that may or may not be useful for you. But anyway, I think everyone's going to notice the pattern here, right? We're going to be adding 5 each time. That's an arithmetic progression. So at face value, we know that since we're adding 5 each time, we must have a 5n in here. But if I tried to do 5n, I would start with 5 and go to 10 and go to 15. And each one of these values are 2 less than 5 and 10 and 15. So why don't I just subtract 2 from everything? And I'm done. All right, great. So we're going to move on to the next one. Again, we're going to assume that the first term is a sub 1, a sub 2, a sub 3, a sub 4. And when we look at the pattern here, again, I think everyone's going to eventually notice that we're multiplying by the same thing each time. This time we're multiplying by negative 3. So this is a geometric sequence. And I'm going to put a negative 3 inside parentheses. Those parentheses are definitely required, raised to the n. And then when n equals 1, I get negative 3. And when n equals 2, I get positive 9. And wait a second, that's not giving me any of these values. First of all, a sub 1 is supposed to be 5. It's also supposed to be positive. So let's adjust this. Let's say that if we subtract 1 from this, then we would get 1 and then negative 3 and then positive 9, etc. for n equals 1, n equals 2, n equals 3. And that's at least starting with the positives like this one. But notice that instead of a 1, I have a 5. Instead of a negative 3, I have a negative 15. Instead of a 9, I have a 45. What do I have to do? I have to multiply each one of these values by 5 to get to these values. So just plop a 5 in front of there, and we're done. Okay, so we can kind of reason our way through that. I hope everyone recognizes these values. 1, 4, 9, 16, 25. They're just perfect squares. We're going to take whatever our input is, whether it's 1 or 2 or 3 or 4 or 5. We're just going to square it. N squared is that sequence. Okay? This one's going to be a little harder. Okay? But my hint to you is consider things like squares. Well, things like squares are maybe cubes, perhaps. If I look at 1 cubed, 2 cubed, 3 cubed, 4 cubed, that's going to give me 1 and 8 and 27 and 64. And we should be familiar with these numbers. And then when we look at these numbers, oh, wait a second. Nope, I put the 3 in the wrong place. I looked ahead and I was thinking about 3s. These might come in handy maybe somewhere else. Yeah, we'll save these for later. Got a little distracted, got a little ahead of myself. We'll save those for later. Instead, let's try another familiar sequence. Instead of putting the 3 in the exponent, let's put the 3 in the base. 3 raised to the 1, 3 raised to the 2, 3 raised to the 3, 3 raised to the 4. Okay, these are also familiar values, right? 3 and 9 and 27 and 81. Unfortunately, they're not these values. Instead of 3, we have a 4. Instead of a 9, we have a 10. Instead of a 27, we have a 28. Instead of an 81, we've got an 82. Well, we just need to adjust all of these by, of course, adding 1. So we will take that original geometric sequence of 3 raised to the n, which creates almost the sequence we want, and just add 1 to each one of them. Okay, so just playing around with the numbers, and if you find some numbers that work, then great. When we have a fraction, like a sequence of fractions we have here, we want to, oftentimes at least, consider the numerator and the denominator as distinct sequences. So let's think about a sub n as being one sequence over another sequence. Well, if n equals 1, our numerator is 2. If n equals 2, our numerator is 3. When n equals 3, our numerator is 4. What's the pattern? We take n and we do the same thing each time to get that numerator. We take n and we add 1, of course. Now in the bottom, instead of adding 1 each time, we're going to be adding 2 each time, right? The common difference here is 2. These are both arithmetic sequences. This time, instead of adding 1 each time, we're adding 2 each time. So we've got a 2n, but of course, then I'd have 2, 4, 6, 8, 10, but I have 1, 3, 5, 7, 9. All of those are 1 too small, so I'll drop this by 1 so that they match. And again, this is just kind of reasoning your way through it. All right, this one is perhaps something we might recognize. They all have a natural log, so let's focus on that 1 and the 2 and the 4 and the 8. Well, 1 is 2 to the 0, 2 is 2 to the 1, and 4 is 2 to the 2, and 8 is 2 to the 3. So this must be a sub n equals the natural log of 2 to the n. But wait a second, that's not quite right, because I don't start with ln2, I start with ln1. So I want to make sure that I'm raising to the 0 power, even though my n value starts at 1. So if I plug in 1 and I want this to be 0, I better subtract 1 from it. And that's going to shift things. I leave this as a challenge to you. Determine whether the sequence is arithmetic, geometric, or neither. I'll give you a hint. It's not neither. That's a fun little exercise. See what you can come up with. And if it's arithmetic, come up with a common difference. If it's geometric, come up with a common ratio. Anyway, this last one is a bit of a tricky one. I kind of got you a little bit started here, I think. Maybe not. No. I guess we're just not using perfect cubes at all. These still kind of remind me of the values that we saw up here. If you recall, the 3 to the n is equal to 3 and then 9 and then 27 and then 81 and then 243. We're just multiplying by 3 each time. And these numerators remind me of these numbers. First off, I'm going to have a negative 3 here instead of a positive 3, and I'm going to add 1 to it to get that negative 2 that I see right there. Here, if I take 9 and I subtract 1 from it, I'll get 8. Here, if I take that and I change it to a negative 27, and I add 1 to it, I'm going to get negative 26. That's going to be that one. And then if I take that 81, I'm going to subtract 1 to get the 80. And if, again, I flip the sign here to get to negative 243, I have to add 1 to get up to negative 242. So I seem to have this pattern down. It's not 3 raised to the n, is it? It's negative 3 raised to the n. And that's going to give us the negative 3, and then the positive 9, and then the negative 27. But then we also have to alternate adding and subtracting. So sometimes I want to add 1 and sometimes I want to subtract 1. And I think we've seen that before with a negative 1 raised to the power, right? We want to make sure we start with a positive 1. So let's make sure if n is odd, we want to flip that exponent to even. And if you play around with this, you're going to see that this is actually going to give you this sequence of numerators. All right? So that means that a sub n is equal to a fraction where the numerator is negative 3 in parentheses raised to the n. The negative has to be inside the parentheses, folks. And then we're going to alternate between adding and subtracting 1 from those values. Very, very tricky problem. If you got that, I'm impressed. We're We're only halfway there, though, because we have to figure out what the denominator is as well. And the denominator is 1, 2, 6, 24, 120. Now, I feel like I've seen those numbers recently. In fact, what are we doing here? We take 1 and we multiply that by 2 to get 2. And then what do we have to multiply to get to 6? Well, 3, right? And then we multiply by 4 to get the 24. And we multiply by 5. We're just multiplying by all of the integers. And that's what factorials are all about. So this is a good one to memorize. 1, 2, 6, 24, 120. Kind of like the way you might recognize 1, 2, 4, 8 as powers of 2. Or you might recognize 1, 4, 9, 16, 25 as perfect squares. You should start trying to recognize these guys as the factorials. Now, the next question is, does this converge? Well, if we remember our hierarchy of infinities, factorials beat exponentials. So because a to the n is always going to be less than n factorial for large values of n, this sequence, it actually converges, right? The smaller numerator means that it's going to converge to 0. Right? And again, that's not mathematically rigorous, but it's good enough for this purpose.